Welcome to session 11, and in this session we want to continue our discussion of subnetting. In order to frame the discussion, however, I'm going to use an analogy, and please note that this is my analogy, and so I want you to respect the intellectual property, and whenever you make reference to this, please remember that Sir Scarlett did this. So here we go. We have a robot called Timmy who is in charge of a conference room. And based on his AI programming, Timmy is supposed to make appropriate use of this conference room. He wants to ensure that the resources are being used optimally. There's only one issue, and that one issue is that Timmy is only able to communicate in terms of binary. And this will become important later down. In order to make use of the conference room efficiently, Timmy has come up with what he thinks is a brilliant idea. Instead of using the conference room and allocating it to just one event, he has decided that he wants to be able to allocate it to multiple events at the same time. In order to do this though, Timmy would now have to divide the room into different sections and allocate each section to the different persons who are renting the space. The capacity of the conference room is 256, meaning it can only hold 256 chairs. And the chairs are labeled starting from 0. And Timmy has decided that in order to show some sort of ownership, he's going to put a T before the number. So therefore, the first chair is going to be labeled as T0. And because there are 256 chairs, then it means that the last chair is going to be T255. Reason being, 0 to 255 will give us 256 different chairs. So that's how Timmy has organized things, and he now wants to go ahead and start to divide based on how many persons indicate that they want to use the conference room at the same time. So if nobody is going to use a conference room, then obviously no chairs are going to be allocated to the conference room. If one group decide that they want to use the conference room at that particular time, then it means that all 256 chairs can be allocated to the room because no one else is using it. But what if two persons or two different groups wanted to use it at the same time? Then what Timmy would do is to divide it into two sections, and then he would equate the chairs, or he would allocate the chairs equally to both sections. And Timmy would have to do this because, remember, Timmy only understands binary. So if two groups wanted to use the room, then the question is, how many chairs are going to be allocated to each section or each division? And if we divide 256 by 2, then that will tell us how many chairs. So divide 256 by 2 and tell me what you get. And you should have obtained 128. So what it means is that Timmy is going to allocate the first 128 to one partition and the second 128 to the other partition. So he divides it in two and puts 128 chairs in one section and 128 chairs in the other section. However, Timmy has also decided that in order to prevent confusion, he wants it to be clear which conference room is being used by which group. And he has decided that he's going to use the chair or a chair to mark the room. He then decides that the chair that he's going to use to mark the room is going to be the first chair within the range. So remember, there are two groups. He's going to put 128 chairs in each room. Each chair is labeled from T0 to T55. So therefore, in the first room, Timmy is going to ensure that T0 is going to be on the outside. So then the question becomes, what is going to be on the outside for the second room, the second partition? And the answer is going to be T128. And if you are asking the question, why is it going to be T128? Then the answer is very simple. Because we started at T0, then it means that 0 to 127, those chairs would be allocated to the first partition or the first section. And then from T128 to 255, those are going to be the chairs which are allocated to the second section. So what Timmy is going to do, he's going to take two chairs, one being T0, and put that at the outside of the first section, and the other one being T128, and he's going to put that at the outside of the second section. It therefore means that out of the 128 chairs, we're only left with 127 usable chairs. But there's another thing that needs to be contemplated. Because Timmy knows that he has to have a security personnel who is assigned to each room, to each section. And so Timmy has decided that he's going to allocate a chair for that person. And the chair that he's going to allocate is going to be the last chair within that range. So therefore means that for the first partition, Timmy is going to have that chair for the security personnel as being 127. And it therefore means that for the second section, he's going to have that chair that is labeled T255. So it therefore means that out of the possible chairs which can be allocated to each section, there are two chairs which are not going to be used. One of them is going to be used to represent or identify the room that the persons must go into, and the other one is going to be assigned or allocated for the security personnel, so that the rooms can be secured. Now what we have just done here is a preview into what is actually happening when we think of subnetting. Because what's a subnet? A subnet is when we take an IP address range and we break it up into different divisions. And we treat each different division as if it is a separate network. Going back to the analogy, it is one conference room that has a capacity of 256 chairs. However, we can divide this conference room into different partitions. And by dividing it into different partitions, we can make better use of the chairs and of the room. So we have one conference room, but in the example that we just used, we're dividing it into two rooms. So those two rooms would now be subnets. We could also divide it into four rooms. And then we would have to decide how many chairs to put into each room. And once again, because Timmy is binary, it means that he would only be using binary computations to determine how many chairs are going to go into each room if he divides this conference room into four sections or into four rooms. So that in essence is what subnetting is about. It is taking an IP address range and dividing it into different sections so that we can treat each section as if it were a different network. And in doing this, we have to determine how many valid IP addresses are going to be in each of these subnets. Another thing that you need to bear in mind is the special use of the chairs that we had used in our analogy. Because when it comes to subnetting, and we have creating these subnets, then the first address in the range cannot be placed on a host device. And also the last address within the range cannot be placed on a host device, because these two addresses are used for special purpose. The first address is always going to represent the network ID. So the first address is network ID. And the second address is going to represent something known as the broadcast network. So we are concerned about keeping track of the first IP address within the range and the last IP address within the range. So it therefore means that out of the total capacity, the total chairs, two are not going to be used. Similarly, out of the total IP addresses which are assigned to a subnet, there are two of them which are not going to be used. The first one, because it represents the network ID, and the last one because it represents the broadcast ID. Therefore, the total usable chairs or usable IP addresses is going to be 2 to the n minus 2. Now you're probably wondering where this 2 to the n come from. So let's quickly jump up to here. When we have a certain number of bits, then 2 to the n tells us how many distinct patterns we are going to have. So if we have 4 bits, well, let me start with 2. If we have 2 bits, and let me do this. So that it becomes clear what is happening. I'm going to go back to truth table. Alright, so in our truth table, we have one of two possible values. We have true or we have false. So let's say I have A and I have B. So these are 2 bits, bit A and bit B. And we're looking at the possible combinations. Then we can have true and true. We can have true and false. We can have false and true. Or we can have false and false. So these are the possible combinations that we can end up with if we have only 2 bits. Just changing the heading so we can have some distinction. So these are the possible combination. Is either A is true and B is also true, or A is true but B is false, or A is false but B is true, or both A and B are false. These are the only possible combinations we can have if we're talking about 2 bits, because a bit can only represent 2 possible states. So how many different combinations do we have here? We have 4. 1, 2, 3, 4 different combinations. If we switch the true for 1 and we switch the false for 0, then what we end up with is 1, 1. So that's 1, 1. Then we end up with 1, 0. Or we can end up with 0, 1. Remember, wherever we say a true, we put in a 1. Wherever we say a false, we put in a 0. Or we can end up with 0, 0. So once again, those are the possible combinations that we can end up with. And if we count them, there are 4 possibilities. So therefore the maths work out. 2 to the n, because in this case, how many bits do we have? We have 2 bits. So 2 to the n being 2 bits, will give us 4. That's 4 combinations. If we expand this, and we say we are now dealing with C, for example, and the question then is asked, how many unique patterns can we have with 3 bits? Then it's 2 to the n is the number of bits, so n in this case is 3. So 2 to the 3 give us 8 possible combinations. And if we take our time and go through it, we will get all 8 combinations. So 0, 0, 0 would be 1. 1, 1, 1 would be 1. We'll also have something that looks like this. 1. Let me grab this line. Would also end up with something that would look like this. 1, 0, 1. That's a different pattern. So that's a different pattern from the rest of them. We also can end up with 0, 0, 1. That's not there as yet. And if we did them in order, then it would have been easier to see what they were, because we would simply run from 0 up to 7. 0 to 7 would give us 8 distinct patterns. So I have 1, 2, 3, 4, 5, 6. So there are 2 others that we have not yet accounted for. And I can see that one of them is going to be 1, 1, 0, because we don't have that as yet. So this one is going to be 1, 1. And then there would be one other one. I leave that to you to figure out which one is left off. Remember, as I said, if you start from 0 and go up to 7, and you look at all the different patterns, then you should account for all 8. So it is important to note that 2 to the n is going to become a formula that you're going to use very often. Now, with the table that we have constructed, it gives you an easy way of thinking about subnetting. If you know the number of bits that you're working with, once you have outlaid this table, then you can simply look at 2 to the n, where n is the number of bits, and you will instinctively know how many patterns you can get. For example, if I have 2 bits, then I'll be looking in this column. 2 to the 2, so that exponent there is going to be the number of bits, and that tells me that I have 4 distinct patterns. If I have 6 bits, then I look at 2 to the 6. And when I look below it, then it tells me that I have 64 distinct patterns. So that is one way in which we can use a table to assist Timmy, or to check if what Timmy is doing is making sense. So going back to what we had attempted to do earlier. It's 256 chairs. He wants to split this room in half. And if he splits this room in half, then the question is, or the question was, how many chairs are going to be allocated to each section? Well, we're working with 8 bits. And out of the 8 bits, we are going to be using 7 bits. Why? Because 2 to the 8 would give us 256. But we already know that we don't want to have all 256 chairs in one location, because we are going to divide this conference room into 2. So what we are going to do then is we are going to use that 1 bit to represent the fact that we want to divide the conference room into 2 sections. Why 1 bit? Because if we want 2 sections, then we need to use 1 bit. Because 2 sections, if we look here, 2 sections can be created by 1 bit. So 2 to the 1. That tells us that 1 bit allows us to create 2 sections. Well, if out of the 8 we use 1 bit to represent 2 sections, then how many bits are we left with? Well, there were 8 bits, we use 1, so we are left with 7 bits. So if we are left with 7 bits, then the question now becomes, how many chairs are allocated to each section? 7 bits, so we look at 2 to the 7. 2 to the 7 give us 128. So we know that the total number of chairs allocated to each section has to be 128. Now, out of that 128 chair for each section, then the question becomes, how many usable chairs do we have for the persons who are coming to the event? Remember, there are 2 chairs out of the 128 that are allocated for special use. The first chair and the last chair. So we would subtract those, or subtract 2 from 128, and then we will end up with 126 usable chairs that we can now allocate to the patrons who are coming to the event. So I stop here, and then in the next one we will continue by looking at a concrete example. But this illustration, this analogy that was just used, pretty much sets up the framework of what is going to happen when we are trying to do subnetting.